sharing. Okay, so we have just learned about complex numbers, and now we're going to learn about what we can do with them and how we can use them to figure out useful things about our quantum states and use more, I guess, granular quantum operations that allow us to tune state. So one of the important operations we're going to learn about is complex conjugate. So complex conjugate is an operation that changes the value of the imaginary component of a complex number. So if we have z is equal to a plus bi, then we're going to define our complex conjugate as a minus bi. So all these things are going to work together to create operations for us, and these operations will help us confirm that a operation is reversible. It'll help us confirm that we can have we can convert between a ket notation and a bra notation. So all these things, we're just going to introduce the operations, and then we'll see how they work together to help us transform quantum information. So first of which is the complex conjugate operation. So complex conjugate, what we simply do is we just take a complex value. So we have a minus bi, and then we have a plus bi, and then we're going to change the imaginary component so that it becomes negative. So it flips the sign of the imaginary values. And we oftentimes see this notation where a hat on top of a variable indicates a complex conjugate operation. So as a note, if we have a complex number, or if we have a number that's not complex, so it's just a positive number, just a real number, it's equal to its complex conjugate. So this is going to be very important for us with why we were able to, previously when we were just working with real numbers, why we never had to worry about any of these operations. Because if we had a number that was a real value, it would be equal to its complex conjugate. And that's because if you have a plus 0i, the complex conjugate of that would be a minus 0i, and plus 0 minus 0, that's the same thing as just your value itself. So let's do a couple of examples of what complex conjugate looks like with specific complex numbers. So we have z is equal to 8 plus 3i. So our complex conjugate of that, we would simply just take the imaginary value and make it negative. So if we have c is equal to 12 minus 7i, the complex conjugate of c would be equal to 12. So it looks like we have a mistake here. So this is actually supposed to be plus 7i. All right, so we have a negative 7i, and the complex conjugate here would be a plus 7i. So let's make a little bit more of a complex structure, since we're starting to work with all these superposition states, and that superposition kind of splits itself sometimes between two basis states. If we have, it splits itself on probability amplitudes that have complex portions. So we have a 1 plus I over square root of 2, so all of that over square root of 2. The complex conjugate of that would be 1 minus I over square root of 2. All right, so the next linear algebra operation will become very important to us. So transpose, that is a way that we can take a matrix or a vector, and it allows us to exchange the information between rows and columns. So what you're simply doing is you're drawing a line. So in these examples, you're simply going to draw a diagonal line, and you're going to flip around that diagonal. So you'd have a diagonal here, and you have a diagonal here. So you could see that whenever we're looking at the transpose of a vector, we just flip around the diagonal. So A0 stays the same, but then A1 flips up. So we can create a row vector from a column vector. And then here we're going to see the exchange between A1 and A2. So A2 goes up to this top right corner, and A1 goes down to this bottom left corner. So this would be an example of transpose operation. So it allows us to adjust the rows and columns for a matrix, and we're going to use this on our quantum states and our quantum operations. So oftentimes when we're looking at transpose operations, we have this T, this capital T, and that indicates transpose. All right, so an example of that, if we have this state M, we're going to, or this matrix M, we're going to look at the matrix and calculate the transpose. So what I like to do whenever I'm trying to do a problem, when I'm trying to like calculate a transpose, I just like to draw my diagonal and flip across the diagonal. So I want to mirror everything on that. So I would go ahead and write my elements that are on the diagonal. So I have 2 and 9. And then I would go ahead and put a 1 up here and a 5 here. So all those values are going to switch over. So we can go ahead and confirm that that is the answer there. So we just did our transpose like that. Okay, so this one's a little bit more complex because it's a matrix that is not a square matrix. So how would you calculate the transpose of matrix U over here? So we could follow the same procedure. So we're going to draw our diagonal, and we're going to just exchange everything across that diagonal. So I will define a new matrix, so U, and I'm going to make it a T to indicate that I took the transpose of U. And that's going to first, we'll think about it. If we have a 2 by 3 matrix and we're exchanging the rows and columns, that's going to give us a 3 by 2 result. So I'll start filling out my known values. My known values are going to be those values on the diagonal, so 1 and 5. Then I'm going to go ahead and exchange my row and column information. So we have 4 and 2. And then sometimes it gets a little tricky when you have these matrices that don't have rows and columns that are even, so like you don't have a square matrix. But what you're simply going to do is just take those values and flip them across the diagonal just like you would do with everything else. So that would be 3 and 6. So this would be our transpose for our matrix U. So we can go ahead and check that out. And finally, we can calculate transposes of vectors. So vectors, once again, you would draw your diagonal, and that would simply just be taking a column vector and making it into a row vector, and vice versa. So here we would have the transpose of our vector V here. So we just are simply taking it, flipping it across the diagonal to create a row vector. All right, so let's go ahead and do an example. In this practice question, we're going to calculate the transpose of this following matrix. So think about what we've learned. There's a couple of answers that are thrown in here to kind of try to trip you up because we've been talking about a lot of different things. So go ahead and try to calculate the transpose of this matrix. So we have a couple different options. So I'll give you all like a minute to do this. All right, so it looks like we have C as our most popular answer. And we can check this out. Let's try. So we're going to go ahead and write our diagonal and then flip everything. So we'll start with our known values. So 2 and 6, our values on our diagonal are going to stay the same. We are exchanging our rows and columns. So we know it has to be one of these two. This is just a red herring. And then we want to we don't really want to add, since we're just calculating transpose, we don't want to add imaginary values here either. So we'll go ahead and flip around our diagonals. That'll give us 9, 0. So we have 9, 0, and then 8 and 3. So we can see our answer here is going to be C. Okay, so now this is where we're starting to get a little fancy. So we have our complex conjugate. Simply take the negative, or we take the negative of our complex part of our values. So if we have a complex number, we take the imaginary portion, we flip the sign of it. And then we have a transpose. So we flip things around a diagonal to exchange the row and column information for a matrix. So let's look at what that would look like for us. So we know that we have a column vector, and we use this dagger symbol to indicate a complex conjugate or complex transpose. And if we think about it, we've seen this symbol before. We've seen this symbol when we were talking about unitary matrices and how we had this special symbol also associated with the inverse of a unitary matrix. So we're going to be working with that a little bit more in the next couple of slides. So we have this dagger that indicates a conjugate transpose. So we take the transpose and then the complex conjugate. So we take the transpose and complex conjugate. What that looks like if we're working with those values. So we know that this hat means complex conjugate. So if we have all these complex values, we're simply flipping everything across the diagonal, and then so flipping everything across that diagonal, and then flipping the sign of the complex portion of these values. So let's work on a few examples. So we have v is equal to 1 minus I, 0, 3 plus 4i, 0. So what would the complex conjugate of this vector be? Well, we would take the column vector, transform it into a row vector, and then flip the sign of all of the imaginary portions of those complex numbers. So we would have 1 plus I, 0, 3 minus 4i, 0. So here we have our matrix here, M. So 3i, 1 plus I minus 5i. So we have the complex conjugate, or that we take, and then we take the transpose. So we take all of our imaginary values, we flip the sign, and then we also flip around the diagonal. So let's say we just draw our diagonal and exchange the row and column information. So let's do another example. What is the conjugate transpose of the following matrix? Okay, so it looks like we have most everyone responding with B, which is the correct answer. So just so we can see this in action, we're once again going to just draw our diagonal, flip across that diagonal. So we have -2 and 6 are going to be our known values. We have no complex portion of those or no imaginary portion of those numbers, so we don't have to do any adjusting. And then we're going to adjust all of the rest of our values. So 9i becomes -9i, I becomes -I, -3i becomes 3i, and then 8 is just going to be 8. So this is how we get our answer B for our conjugate transpose of this matrix. All right, so now we're going to tie this back to quantum information. So we have, we use kets a lot for representing our quantum state and our column vector notation, but we can transform them into the corresponding part of bra-ket notation using the conjugate transpose operation. So these are referred to as bras. So we have bras and kets that work together, and kets are our column vectors and bras are our row vectors. So both transformations use the same step, and we follow the process of taking the complex conjugate and then the vector transpose. So if we have the ket Z and we want to find the bra representation of that, we take the conjugate transpose. So that's just complex conjugate and transposed, all wrapped up in this one symbol of the dagger. So let's do an example of that. So let's say we have ket 0 and we want to calculate the corresponding bra that represents ket 0. Well, we just simply take the conjugate transpose. We don't have any complex aspects of this state. So that becomes 1, 0 in a row vector notation. Now we have a little bit more of a complex state here. So because we have imaginary numbers. So here we have ket psi, which is going to be 0, -I. And we want to find the bra notation of that. So this is going to be equal to this row vector 0 and then I. So we took the transpose and the complex conjugate to get the following. Now we're going to take our superposition state. So we just learned about this state. This is actually our ket I state, if we wanted to think about our Bloch sphere. And we're going to find the corresponding bra notation for ket phi. So we take our, in this case, we're going to take our transpose to transform it into a column vector. And then we're going to flip the sign on our complex portion, or the imaginary portion of our complex number. So we have no imaginary portion for the first element, but here we have an I, so we need to make that negative. So if we were wanting to convert from a bra to a ket, we follow the same procedure. So we take the conjugate transpose in order to get the corresponding ket for a row vector bra. So let's do an example. So here we're going to convert ket 1, 0 to bra 1, 0. So this one's a little tricky, so we'll go ahead and see what y'all think about it. So remember what our ket notation stands for. It's going to be a column vector. So go ahead and try this problem out. All right, so we have most folks responding back with D, and we can go ahead and work this out. So we know that we have the following column vector. So we have the binary value of 2, so we can do 0, 1, 2, 3 to figure out our column vector with that easy little trick. And then we want to convert it to the bra notation. So we'll take the transpose, 0, 0, 1, 0. Because we have no imaginary portion to the only element there, we don't have to worry about flipping any sign or anything. So even though we are working with a conjugate transpose, that does not necessarily mean we start adding complex values when they don't exist. So that's why we would not choose answer C. Instead, we would choose answer D. So here, answer D is what we're looking for. All right, outer product. So these are part of some of the mathematics of quantum. So we'll see this in more complex state analysis, but we're going to just go ahead and introduce what these terms are so that whenever in further study, you'll be able to see these terms and know what they mean. And outer product is one way that we just interact our column vectors and row vectors that represent quantum states. So those would be our kets and bras respectively. So outer product is simply going to be whenever you're working with two quantum states, it's defined as taking the ket and multiplying it by the bra representation for your second state. So we indicate it in the following way. And you have to convert for your second state, you have to convert it into a bra notation. So what would that look like exactly? It's going to be an outer product operation. So we're going to take two vectors and expand them into a matrix. So we take two vectors, and the result of that outer product is going to be a matrix for us. So because we're taking the complex transpose of our state phi, we will have alpha 0, alpha 1 for our first state, the complex conjugate of beta 0, complex conjugate of beta 1 for our second state. And we're going to do our matrix multiplication. So once again, for matrix multiplication, when we're combining two vectors, we have the case that we can combine two vectors or two matrices if our inner product, or if our inner dimensions agree. So if we have an n times m matrix, and we're trying to multiply by m times k, as long as these inner dimensions agree. So here we have a 2 by 1 vector, we have a 1 by 2 vector. So we have a column vector, a row vector. We can combine them because these inner elements agree, and because when we do combine them, that's going to form a matrix that's this dimension of the outer elements, or the outer dimensions of both of these vectors. So here we're going to do our same procedure for matrix multiplication, where it's row times column. So we have row times column, and then that's going to produce our first element here. So then we do row times column again to produce this second element, row times column to create this third element, and then row times column to create this last element here. So here we go. This is a ket 0 here, and then we have a ket plus that we are turning into a bra for our outer product. So that would result in the following matrix for us. All right, so now we have inner product. So the inner product of two quantum states is going to be defined as so if we have ket psi and ket phi, we're going to take the bra of psi and multiply it by phi. So we have to once again do our conversion from ket to bra for our phi portion of our of our calculation, and that results in the following. So since we're doing our conversion from ket to bra, we take our conjugate transpose, and then we keep our phi state as is. So what is this going to produce for us? Outer product took two vectors and produced a matrix, but inner product is going to take two vectors and combine them in order to produce a scalar. So the result of an inner product is going to be a scalar or a single value. So let's try this. So I think this is where we got tripped up because I used different values in a different spot. So we have, so let's see if this is correct. So we have our two states that we're trying to combine. So I'll work it out. So we want to take the inner product of a ket plus and a ket 0. So we know that this is going to be our superposition state. So 1 and 1. And then we have a ket 0 state, which is going to be 1, 0. We have to take our conjugate transpose to do our conversion from ket to bra. So that's going to be a 1, 1, 1 over square root of 2. And then a 1, 0. We do our matrix multiplication. So we have 1 times 1. And of course, we have to include our factor of 1 over square root of 2. So we have 1 times 1, that's going to produce a 1, and then we have 1 times 0 plus 0. So we were left with 1 over square root of 2. So go ahead and see this worked out. So we have all our steps. So we're left with 1 over square root of 2. Okay, so now if we are thinking about complex numbers, we have to think about their absolute value in a different way. So previously, when we're working with real numbers, that's just going to be positive numbers and negative numbers. So a absolute value, for example, if you had -3, you would take the absolute value of that, and that's going to be equal to just +3. Well, how does that work with complex values when you're working with portions of -1, so like square root of -1? To calculate the absolute value of a complex value, you have to do the square root of the complex number times its complex conjugate. So let's see what that would look like. So once again, if we're looking at what this means for us, if we have z, and z is equal to a plus bi, we would have an absolute value that's equal to square root of a plus bi times a minus bi. So let's think about that in a little bit more depth too. So if we have, this is kind of similar to some things we've seen in algebra when we're working with binomials. So if we have a plus bi times a minus bi, let's look at what underneath what underneath the square root sign is going to equal to us. So let's FOIL. So we first a squared inside plus b a I outside. So that's going to be a minus b a I. And then last, so we have bi times bi, so that's going to be b squared. I squared is equal to -1. -1 times -1 is going to be equal to +1. So we end up having some terms cancel out. So we have these two terms cancel out. And then we end up getting the square root of a squared plus b squared. So kind of cool. What we just talked about in the previous lecture of even though we're working with complex numbers, we get very real values because whenever we are taking absolute values, whenever we're multiplying things by their conjugate transpose, we end up getting real portions, real values that come from these complex numbers. So even though they have the I value in there, we end up getting real values that are associated with the absolute value. So very similar to how we take here we're taking the square root because we're working with absolute value. But if we're taking the absolute value squared, we would just be left with our terms of a squared plus b squared associated with our complex number z. Okay, so that's just an aside, but we've got a lot of this information here that we'll see worked out through example form. So we have 3 plus 4i. We're going to take the absolute value of that. So it's going to be square root of 3 plus 4i, 3 minus 4i. So I'll write this again. I probably should have left it up a little longer. So we have these two terms, but just to summarize, we have z equal to a plus bi. So we have z times its complex conjugate. That's going to be equal to a squared plus b squared. So I'll keep this here so y'all can go ahead and write it down. So we can take that for our, we'll multiply this all out just to confirm, but we'll see that it's just going to be equal to a squared plus b squared for those portions within the complex number. So let's go ahead and work this out. So we'll FOIL. So we have first, so we have 9, 3 times 3 inside. So we're going to have a plus 12i outside minus 12i, and then last. So that's going to be a plus 16 because we have I times I. That's going to give us a -1, and then we have a negative value associated with the second term. So we have negative times a negative giving us a positive. Well, just like we see here, we have these two terms canceling out. So that gives us a 9 plus 16, and that's going to be equal to 25 for us. And we're not done yet because all we did right here was just multiply a complex number by its conjugate, we took a complex number and multiplied it by its complex conjugate. So now we have to take the square root of that. So we want to still take the square root of this value, square root here, square root here. So that's going to give us 5. So this is how you would find the absolute value of a complex number. So even though we are working with imaginary numbers, we still get very real absolute values associated with them. Once again, if we're wanting to take the absolute value here, give us 36 plus 64, since we have these inner 48ths i's canceling out, which is a square root of 100, which gives us 10. So this lecture I know had a lot of math in it, but we'll tie it back to quantum and like why all these things are important and do more examples next time. So are there any questions before we wrap up?